Welcome to 5.1 and 5.2, where we're going to talk about discrete probability distributions. So, 5.1. This section we're going to talk about random variables, probability distributions, how to calculate the mean and standard deviation, and also, again, about significantly high or low values. Some vocabulary. A random variable. It's just a variable. Usually we represent it with an X. It has a single numerical value. It's determined by chance for each outcome of a procedure. A probability distribution is a description that gives the probability for each value of the random variable. It's often like expressed in the format of a table, a graph, or even a formula sometimes. Now, we already know the difference between discrete and continuous. A discrete random variable has a collection of values that's finite or countable. A continuous random variable has infinitely many values, and the collection is really not countable. So we're going to deal with the discrete or countable random variables right now, and then later on we're going to deal with the others. All right, probability distribution requirements. These three things have to happen or you do not have a probability distribution. Number one, there is a numerical, not categorical, random variable x, and its number values are associated with corresponding probabilities. Number two, you must have the sum of all the probabilities equal to 1. Number three, every probability value must be between 0 and 1 inclusive. So we're going to have to check those three things before we get started to see if anything's even a probability distribution. All right, so our first example, we've got a coin toss here. We're going to consider tossing 2 coins. The random variable we say is x when the number of heads of 2 coins are tossed. And we're going to see, is this a random variable or not? Or a probability distribution or not? So first of all, let's look at our category for x over here. This is x. Is x numerical? And does it have the associated probabilities? 0, 1, and 2 are numbers. That checks. And these are the probabilities over here. Yeah, that checks. So number 1 looks like it's met. Number 2, do we add all the probabilities and get 1? Well, let's add them up and see. 0.25 plus 0.5 plus 0.25 does equal 1. Yeah, so number 2 is met. Number 3, are all of our probabilities between 0 and 1 inclusive? Yeah, quarter, a half, they're in there. So what we're going to do is we're going to check that on the second part here. So number 1, we said that our x random variable is numerical and associated with probabilities. Yep. Remember, it was 0, 1, and 2, and it had probabilities over here. Were our probabilities, the sum of our probabilities, equal to 1? Yes, they were, because 0.25 plus 0.5 plus 0.25 is 1. And our third thing, or is it between each value between 0 and 1 inclusive? I'm going to kind of be sloppy here. But is it between 0 and 1 inclusive? Yes. So that's what we're going to check, all those things in our probability. So let's try another one. See if it's a probability distribution or not. Okay, hiring managers were asked to identify the biggest mistakes that job applicants made during an interview. Here's their table. Is it a probability distribution? So the first thing is, here's x. Those aren't numbers. Not numerical. That's a problem. Okay, is it associated with probabilities? Yeah, it is. All right, number 2, did we break that rule as well? Because we already broke rule 1 because it's not numerical. Rule 2, do these add up to 1? No, they add up to more than 1. So we've broken Rule 2. This is greater than 1. That's not good. And are all the numbers between 0 and 1 inclusive? Yeah, so we broke Rule 1 and Rule 2. So no, this is not a probability distribution. We broke Rule 1 and Rule 2. All right. This one you would practice. We're going to skip that because I think you all can do practice on your own to see if it breaks the rules or not. Some formulas for parameters of a population. So mean or mu for a probability distribution is the sum of x times p of x. The variance is the sum of x minus mu squared times p of x, the probabilities. This one here is one you'll probably want to use for calculating. You'll take x squared times p of x, sum that, and subtract mu squared. And over here, the standard deviation is the square root of your variance. Some round-off rules. I'm not real picky about this, but my math lab is. Round results by carrying one more decimal place than the number of decimal places for the random variable. If your values are x values are integers, round the mean, standard deviation, and variance to one decimal place. Okay, let's practice finding these things. If this is a probability distribution, first we've got to check that. Identify the mean and standard deviation. If it's not, say which ones did not meet. So let's find out if it's even meeting a probability distribution. Okay, x, those are all numerical. Looks like they're all probabilities over here. Okay, that meets Rule 1. So number 1, check. Number 2, let's add these all up and see what we get. So 0.031, 0.156. I'm happy adding. Sorry, my calculating is kind of slow here. And I get exactly 1. So rule number 2 is met. Rule number 3, are all of our probabilities between 0 and 1 inclusive? Yes, they are. So it is a probability distribution. So yes, he is. Now we have to find the mean and standard deviation. Now the mean, the formula for that is mu is the sum of your x times your p of x. So I am going to take each one of these and multiply them together, x times p of x, and then add the answers together. So I'm going to take 0 times 0.031 plus 1 times 0.156 plus 2 times 0.313 plus 3 times 0.313 plus 4 times 0.156 plus 5 times 0.031, and I get 2.5 for my mean. Okay. All I did was multiply the x times the p of x and add it all together. Now, how do I get the standard deviation? And that is sigma, and he is the square root of the variance, which is the sum of my x squareds times p of x minus my mu squareds. Okay, so I'm going to square all of my x's. So I got to square these first. So I would actually probably write x squared over here. 0, 1, 4, 9, 16, 25. They're going to multiply by p of x. And then I'm going to subtract mu squared. Well, if mu is 2.5, mu squared is 2.5 squared. I'm just going to keep that in mind. So in this thing. I've got a big, huge square root, and I'm going to be doing 0, because 0 squared is 0, times 0.031, plus 1 squared, that's 1, times 0.156, plus 2 squared is 4, times 0.313, plus 3 squared is 9, times 0.313, plus 4 squared is 16, times 0.156, plus 5 squared is 25, times 0.031. Okay, there's 25 right there, 0.031. And that's all of that added together minus 2.5 squared. That's mu squared there. And then I'm going to square root that answer. And I actually get 1.1 when I type all that in and square root it. It's a lot of work, but yep, that's how you do it. Okay, if you want some more practice, here's another one to see if it meets the requirements. And then you will also find the mean and standard deviation. When I worked this one earlier, I found the mean to be 0.4, and I found the standard deviation to be 0.6. So if you want to practice this one with this table, feel free to. This 0 plus is basically 0 when we're using that. It just means it's barely above 0. It just has like 0 point with a bunch of zeros after it. So it's basically 0 when you're doing calculations. So that's if you want to practice some. Let's move to expected values. There's a formula for expected value. It's a capital E for expected value. And it's basically your mean of your discrete random variable. And it says it's the sum of x times p of x. So this one here, find the mean and standard deviation of girls in 8 births. Again, I think that's just you getting some practice, so we're going to skip that for now. If you want to do the mean and standard deviation for your own practice off this table, the mean is the sum of x times p of x. I got 4.0. And if you're doing the standard deviation, I got for that one 1.4. So you can practice this on your own if you'd like to. Make sense of your significant values. Right here is the main idea. Your mu is in the center. 2 standard deviations to either side, so plus 2 sigma or minus 2 sigma, makes it either significantly low or significantly high. Anything in between those two values is not significant. That's what you need to know. And what do we do with this? If we know something's significantly high or significantly low, we could sit there and see about the probability of so many successes. We also have that it's 0.05. That's a kind of general rule, like our 5% rule. So if we have something that's in the upper or lower 5%, then that's going to tell us if it's significantly high or low. Now this one here says we're going to use the range rule of thumb to determine whether one girl in 8 births is significantly low or not. So one girl in 8 births, we want to see if that's significantly low or not. So how do we do that? Unfortunately, we need to know mu plus 2 sigma or minus 2 sigma, so we need to know mu. Mu is the mean. And we know that's the sum of our x times p of x. So we would literally multiply these numbers together and add them all up. And I'm going to do that. 0 times 0.004 plus 1. And you get the idea, all the way to 8 times 0.004. And I get that to be 4.0. So we're going to multiply those together and add them all up. That's what we do. Now for sigma. Now sigma, we know his formula. It's the square root of the variance, which is the sum of our x squared
At this time, we need
times
all
p of
7th graders
x
to go to the gym for group pictures. All 7th graders.
minus mu squared. So what we would do is we would square these numbers, 0, 1, 4, 9, 16, 25, 36, 49, and 64. Take the square times the p of x and then add them all up and subtract 4.0 squared. In this case, I get 1.4. Now, I'm going to use that idea of that significant, not significant kind of thing. So, mu is 4.0. And if I go significantly low, because that's what we're asking about, is the low, that's 2 sigma that way. So 4 minus 2 times 1.4. 2 times 1.4 is 2.8. Subtract that, that's 1.2 is the boundary line. And this part is low. And then I'm going to go to the other side, just so you could see how to do that. That'd be 4 plus 2 times 1.4, so plus 2 sigma. And that's 2.8, so 6.8 would be the high. It didn't ask us in this question, but you need to know how to do that anyway. And anything in between is not significant. So we are looking at the boundaries between 1.2 and 6.8. That's our boundaries here. To see, is he low, not, or high? And our question is he low? So 1 girl in 8 births. 1 girl in 8 births. I'm going to go to my table. That probability is 0.031. Is 0.031 smaller than 1.2? 0.031 is smaller than 1.2. That's that number there. So yes, this is a very significantly low. So yes, it is significantly low to have 1 girl in 8 births. Now, could we check to see on this for the next question? Is it going to be significantly high to have 6 girls in 8 births? All right, well, I'm going to go back to, I'm not going to do all this work again. We already know mu is 4.0. And we already know sigma is 1.4. And if I have my little drawing a moment ago, we know that 4.0 is here in the middle. And to go on the left for low, 4 minus that be 1.2, remember. And then to go on the high, 4 plus 1.4 times 2 was 6.8. So we knew that this part in here was the naught, okay, between 1.2 and 6.8. Now our question was about high, so we're going to go to our table. 6 girls' births is 0.109. Is 0.109 greater than 6.8? Is 6 girls greater? Sorry, I don't know why I put the probability. I want 6. I did that on the last problem too, didn't I? 6 girls, is that greater than 6.8? The answer is no, it's not. So this is not significantly high, because 6 is not greater than 6.8. Sorry guys, I should have done that on the last one. I should have done is 1 smaller than 1.2, and it was. Hope I didn't confuse you too bad. I'm so happy looking at the table. All right. So now here's where we're going to be using the probability using our table. So we've got a table and the probabilities again. Notice how these problems are a little bit different than what we just did. Find the probability of getting exactly 6 girls in 8 births. So the probability of exactly 6. Go to my table. It's 0.109. Okay. Part B, probability of getting 6 or more girls. So probability that I get X greater than 6. 6 or more. So 6 or more is this group here, 6, 7, or 8. So I'm going to add their probabilities together. 0.109 plus 0.031 plus 0.004. And I get 0.144. Okay, part C. Probability is relevant for determining whether 6 is significantly high number of births in 8, and is a result from part A or part B. So we want to know probability for determining whether 6 is significantly high. So that's like the probability of X greater than equal to 6. I'm using that because it contains the outliers. So I would use the answer to part B. I wouldn't use the answer to part A because it's exactly 6. All right, the next one. Is 6 significantly high? Why or why not? So let's see. The probability of exactly 6 is 0.109, and that is 0.109 is that less than 0.05. Remember that, 5% rule I mentioned earlier? Is that smaller? No, it's not. So no, 6 is not significantly high. So this is another way to tell about significant high, significant low from the chart. You could do mu plus 2 sigma or minus 2 sigma, or you could use the 5% rule. All right, now this one is basically the same thing, except it's talking about significantly low, so you could get some practice in here. Part A, the answer I got is 0.031. Part B, the answer I got when I added all those together is 0.035. Part C, again, because of the outliers, you would use part B. And part D, is it significantly low? The answer I got was yes, because 0.031 is less than the 5% rule. So those, if you want to practice one on your own, here's you a practice. All right, now we're going to look at 5.2. 5.2 is going to be concerning with the binomial probability distribution. So the binomial distribution. And he's special because bi means 2. So he has 2 categories, of success, failure. Like heads, tails, acceptable, not acceptable, defective, survived, died, those kinds of things. It also has 4 things that are requirements of a binomial. One is a fixed number of trials. Number 2, the trials are independent. Number 3, the trials have 2 categories. And number 4, the probability of success
we have 8th graders go
must
to
be the same
gym
for all.
Group pictures, all 8th graders.
Okay. Now, I remember these things a little bit differently. Sometimes it helps because, an acronym or something. The fixed trials, they have to be independent, 2 categories, and the probability of success has to be the same for all. That makes a binomial distribution. If any of those fail, it is not a binomial. So, some notation and some way to remember it. Remember, I said the number of trials is fixed. N. Independent trials, I. 2 outcomes, B. The success is constant. So I use the little idea of bins. Now, here's some notation. P is going to be your probability for success. And again, what do you want to define the first one as success? The opposite or complement is the probability for failure. And then N is going to stand for the number of trials. And X is going to be your number of successes. Okay, let's see here. We first all got to check to see if this thing here is a binomial distribution and then identify all of our values if so. So we have an adult is randomly selected. There's a 0.85 probability this person knows what Twitter is. Suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. Is this a binomial distribution? Well, we know binomial distribution. I told you that was bins. So I'm going to write bins over here, and we're going to check all that. Bins. We know that there has to be 2 outcomes. So I'm going to look to see, is there 2 outcomes? B means 2 outcomes. Yeah, we have a 0.85 probability they know, so that's P. So they also ask us down here to identify everything. So P is going to be 0.85. That's a probability of success. So that means his complement, that means you don't know what Twitter is 0.15. That's Q. So B is checked off. I is the independent trials. Well, yeah, that's independent because it doesn't matter if I know what Twitter is. That's not going to affect you knowing. So I is good. N is a fixed number of trials. And it says exactly 3 out of 5. So N is 5 trials. 5 adults are randomly selected. Now my last one, S. S over here is talking to us about sorry, I can't even speak today. S is talking about us having all the probability of success being the same. And yes, it is. It's the same for anybody. All 3 out of 5 of those adults could have that. So our X in this case is 3 adults out of 5. And they're all equally successful at getting them. So we've labeled N, P, Q, and X, and we've made sure that this is indeed a binomial. Now back to the 5%, we have that as well. When sampling without replacement, the sample size is no more than 5% of the size of the population. We can treat these things as independent. You want to be able to do that even though it's not truly independent because it makes the work a lot easier. So we're going to abuse this 5% guideline. We have different ways to find binomial probabilities. You can use your calculator. You can use some tables at the back of the book, and there's a lovely formula as well. There's the formula. Isn't this guy beautiful, guys? N factorial, so n is the number of trials, over n minus x factorial, so n minus the number of successes, then factorial that. X is the number of successes, times p to the x, the probability of success to the number of successes, times q to the n minus x. Oh my goodness, isn't that fun? It's not terrible, it's just lengthy. Or you could use your calculator. I know you guys, Jonathan and Jackson, I know that you can also use some technology on the web, just kind of Google binomial PDF or binomial CDF calculator. But here's what, and the calculator's in our classroom, how you could use it, and I recommend this method, is you use the second vars keys to go to the distribution menu, and you have binomial PDF for your probability distribution function, and CDF for your cumulative probabilities. These are the ones that are the equals, and these are the ones that are like less than or greater than. You enter your number of trials, your probability, and your successes, your NPX, into the calculator with commas between them, and it will tell you and calculate all that for you. So let's go practice some of this. All right, here's by hand, and it's a little nasty, but we can do it. Given that there is a 0.85 probability that somebody randomly selected adult knows that Twitter is, use the binomial probability formula to find the probability that 5 adults are randomly selected. Exactly 3 of them know what Twitter is. Okay, our formula, what I'm wanting to do is I want to find the probability of 3 out of 5 adults know what Twitter is. So our formula was n factorial, so 5 factorial over n minus x, so 5 adults minus the 3 selected, factorial, x factorial, so 3 factorial, times. Then there was p, it's the probability of success, that's 0.85. So 0.85 to the x, which is 3, times q, which is 0.15, that's you don't know, to the 5 minus 3, or n minus x. And you would type this nasty thing into the calculator and hit enter, and you would get 0.138. There's a almost 14% probability that 3 out of 5 people know what Twitter is, randomly selected. Okay? So let's see. This one here is just seeing if you can kind of get the idea. Is this a binomial distribution, and label all of the N, P, and Q? You could go through on your bins, and I recommend you go through and make sure this is indeed, I'm telling you it is. And you can go through and read, see what N, P, Q are in here. This one talks about 80% of teenagers, so that's 0.8. So that means the Q is 0.2. And it talks about your class of teenagers. So I want you to kind of go through and see if you can do this on your own. There's your answers that you're looking for. All right, formulas. If you have a binomial distribution, remember you have to check the bins, B-I-N-S. If you do, the mu is just your n times your p. The variance is n times p times q. And the standard deviation is the square root of the variance. Oh, that is so nice. Nice formulas for once. And again, your range rule of thumb for significant values, mu plus sigma, mu minus 2 sigma. Those are your low and high. Anything in between is not. And you can use also the 5% rule. All right, so this one, we're going to see if it's significant or not is what we're looking at. It says part A, we're finding the mean and standard deviation. Part B, we're determining if it's significantly low or high, what those values are. And then C is we're actually answering whether it is or isn't. So they tell us N is 460 overtime wins. P is 0.05 or 0.5 and Q is 0.5 because you're assuming that you win on a coin toss. It's half and half. So they have both the same chance. Find the mean and standard deviation. Well, mean, we just figured out, has a nice formula. The mean is N times P. N, we said, is 460. Times P, the probability is half a chance, so 230 games. That's your N, or I mean your mean. Now your standard deviation, I'm gonna put him up here. Standard deviation is the square root of N times P times Q. Just the square root of 460 times 0.5 times, well, Q is also 0.5. So if you put all those in there and square root it, you get 10.7 games for the standard deviation. Now part B says use the range rule of thumb to see what the significant high and low values are. So here's my kind of little guy. I know that 230 is in the middle. And this is 230 minus 2 times 10.7. And if I put that in, 230 minus 2 times 10.7, I get 208.6 games or less. And that's for the low. Now if I do the high, that's 230 plus 2 times 10.7. 230 plus 2 times 10.7 is 251.4 games or more. And that's for the high. So part B, it's going to be between 208.6 and 251.4.
At this time, could I get all ninth graders to the gym for group pictures?
Yeah.
All ninth graders.
That says, is the result 252 overtime wins in 460 games significantly high? So 252, is he bigger? Yes, 252 is bigger than 251.4, so yes, it is significantly high. Now, I told you earlier the difference between binomial PDF and CDF in your calculator. This is where you're summing up your x values. This is when you have exactly one. This is the equals, and this is like less than or greater than case. All right, now, I don't really want to do these by hand using that formula. That's the n factorial, all that. So I'm going to skip to the part about the calculator. But if you do these by hand, you will get exactly the same answers we get using the calculator. So what am I going to do? Find the probability that the number of correct answers is exactly 7. So this one would be the binomial, and that's exactly. So it's the binomial PDF, because it's exactly 7 of 8, because there were 8 trials. I was reading the problem, sorry. Times your, or comma, your P, that's 20% for your P, because that's how much you can get correct, and exactly 7. When I put that into the calculator, I get 0.1234, 4 zeros, 8192. It's not a very high probability of getting exactly 7. All right, at least 4. correct. So this one's at least. So that's, and I don't want to do at least 4 because 4, 5, 6, 7, 8, that's a lot. So I'm going to do the complement of that. So 1 minus the binomial CDF, because I've got more than one number here. I have 8 trials. Probability of success is 0.20. And there's 3 numbers that way, because the numbers less than 4 are 1, 2, and 3. So there's 3 numbers that way. That's why I'm using the 1 minus, the complement. In this case, it's 0.056 2816. Now my next one, fewer than 3. That's the same answer as I got on number fewer than 3 is the same thing I'm going to get as number 18 here, where it says no more than 2. Sorry, I was looking at those and I was like, oh, those say the same thing. So 17 and 18 are going to look like this. Again, fewer than 3 or no more than 2 is binomial CDF, because it's not saying exactly. So we've got 8, the success is 20. And how many numbers are less than 3? Well, 1 and 2, so 2 numbers. And so if I put that into the calculator, I get 0.796917776. Now my next one, no correct answers. Okay, that's exactly 0 right. So binomial PDF this time. 8 trials, 0.2 per chance getting it, 0. And that is 0.16777 Sorry, my handwriting's a little messy there. And my last one down here, at least 1 correct answer. I'm going to use the complement because of that, at least 1. So 1 minus the binomial, and again it's CDF, or PDF, sorry, this time because at least 1, if I use the complement, that means I get none. So I'm going to do 8, 0.2 of 0 correct, because at least 1 means all of them, and I don't want to do that much work. So I did PDF of 0 and did the complement. So this is going to be 0.83222784 when I put him in the calculator. And that is where you're going to be left off, and you're going to be working some of these problems in 5.1 and 5.2. You're going to be looking at probability distributions to see if they are. They're going to be looking to see if they are binomial distributions. You're going to be looking for means and standard deviations, talking about a significantly high, low, or not significant values at all. So you have a lot